AP Chem, we have made it to Unit 5. So we are 4 deep through our 12 units. We are going to be getting into the Unit 5 material, which is gases. And I think that gases are generally pretty easy to understand. I think that the material that you're going to learn with this unit is pretty straightforward. The math is nice. The math builds off of your algebra skills and stoichiometry, so it's nothing super crazy. And I think that you're probably really going to like it. So we're going to kind of start off today just talking about how gases behave, some fundamental principles about gases, and then we'll kind of get into it from there. So some things that you need to know about gases, and some of these are kind of obvious and some of these are maybe a little bit less obvious, but gases have a volume. So gases occupy whatever container you put them in. So if I take a gas and I put it into a really tiny container, and then I take that same gas and put it into a bigger container, it will expand and contract to fit the container. And that's because gases have little, if any, intermolecular forces. So when they move around, they are zipping around all over the place, and they are not clustered together like a solid or a liquid is. Solids and liquids have pretty strong intermolecular forces, which keep them tight together, molecule to molecule, and that's why they hold that shape and don't occupy their whole container. Intermolecular forces are strongest in solids, and so since they're holding on really tight, that's why they hold their shape. In liquids, they're a little bit more reduced, and that's why they can expand to the shape of their container, but they won't occupy the entire container. Whereas a gas has very few, if any, intermolecular forces, especially at room temperature, and they kind of fly all over the place and will just expand to fit whatever container they have. So they occupy a volume. We can measure it in milliliters or liters. Depending on the type of calculation you're going to be using, you may need to put it into liters. So just make sure that you're comfortable doing that calculation. When we talk about gases, because they are so spread out in terms of their particles, they do have measurable masses, but usually if you capture some of it, it's pretty small for the volume that you're actually going to be doing some work with. So we're talking about like tenths of grams, not I'm going to weigh out 100 grams of helium. Like, to make that happen, it's either got to be compressed at a really high pressure, or you have to have this mega container of it. So you will be dealing with masses of gas, but again, it's much smaller compared to normal stoichiometry. Like I said, their ability to expand and contract makes them fill up their container, and they also expand and contract based on changes in temperature. So if the temperature changes, your gas will expand or contract. When we talk about gases, you will talk about containers that have fixed volume, which means like I put a gas in a container that has a lid and the container itself cannot change size. So it's a fixed volume. Like I have a 1 liter container. Examples of that would be like a beaker, a jar, that kind of stuff. If we talk about flexible containers in gas laws, that could be like an accordion container that can expand or contract. We could be talking about a syringe, which is like the thing you get a shot with, where it has a little plunger that can move up or down. We could talk about a piston, which is kind of got that same, it's a tube with a movable up and down portion. So when we're talking about things, make sure you know whether we're talking about stuff happening in a fixed container volume or a flexible container volume, because that can change things as well. Balloons are also a flexible container if you think about it, because they can expand and contract pretty easily. So just make sure that when you're talking about gases, you know what type of container it's in. And gases, what is going to be the most important part for them is that they can apply pressure. Now, when you think about pressure, you think about like stuff kind of pushing down on you or pushing down on something or pushing out on something. And that is exactly kind of what pressure is. Pressure is the force something applies divided by the area something is applying that force on. So I always use the example of, let's say you are walking down the hallway and you get your foot stepped on by somebody who's wearing a pair of sneakers. It's not going to feel great. Their force is going to push down on your foot and it's not going to feel nice. But now compare that if that same person would have been walking down the hallway and stepped on your foot with the back of a high heel. Now it's the same force being applied by that person, but divided out over a wider area with the sneaker and a smaller area with the high heel. what you're going to have in that situation is a much higher pressure with the high heel. And that's how you end up in a situation where that would really hurt. Another example of this is like if you've ever heard of anybody trying to show you a trick where they like lay down on a bed of nails. If you look at the bed of nails always has a bunch of nails on them, but they're spaced pretty close together. And what happens is when you do that, your force that's being pushed down on your body or from your body is spread out over all of those little nail points, and it doesn't actually hurt you too bad. If you would lay down on a single nail, all of your force would be applied over that one tiny nail head, and that would be obviously really bad for you and not the best life choice. So when we talk about pressure, the way that it works is that the greater the pressure, the greater the force is being pushed down on that area, or it's a similar force but a smaller area. In terms of like your general existence, the atmosphere around you pushes down on you and applies pressure to you. It is a lot of pressure, but you are generally used to it, so it's not so big of a deal. The more air you have on top of you, the higher the pressure. And then if you dive underwater, that is a higher pressure on top of you even still. Like if you have like dove underwater and you felt the pressure on your ears, that's because the weight of the water is pushing down on you and it's making your ears sensitive. So what happens is if you go to different locations on Earth, the atmosphere will be pushing down on you at different amounts. It is lowest the higher you go. So the closer to sea level you are, the higher the pressure is going to be on you at any given time. And if you go up into the mountains, there's less air and there's less atmosphere pushing down on you, and so the pressure is lower. So even things like cooking work differently up in the higher elevations of like mountain towns and stuff like that, because the air pressure causes different behaviors in things like the boiling point of water. And we will get into that a little bit when we talk in a little bit, but I just want to kind of give you a preview for that. So all of those things are kind of tied together and are caused by pressure. And that's one of the things, like if you go flying, for instance, if you've ever been in an airplane, you can feel your ears kind of feel funny. And that's because as you go up into the atmosphere, the air pressure is very, very low up there. What they do is they actually pump gas into the airplane so that you guys are accustomed to the pressure, but generally it's about 3/4 the pressure you're used to. And so that's why sometimes you can feel a little funny on an airplane. So it's one of those things that you just need to kind of know that the higher up in the atmosphere you are, the less air there is and the lower the pressure is, and the lower down you are, the higher the pressure is. It's one of the reasons actually why athletes train up in higher elevations. It's because their body gets used to working out with less air. And so when they go run a race that's closer to sea level, they've got all this extra oxygen and they can kind of run at a more intense pace because they've got extra oxygen and they're used to being really good with low oxygen. I digress. Okay, so when we talk about pressure is going to kind of be the biggest thing that we talk about here, because pressure is going to cue us in as to essentially how much gas is causing this particular property. The tool that we typically use to measure gas pressure is the barometer. And when you look at like a weather forecast or something like that, you'll see the atmospheric pressure that's registered through a tool called a barometer. Now, a barometer was invented by a guy by the name of Evangelista Torricelli, an Italian guy, in 1642. So it was invented a long time ago. And actually, they name one of the pressure units after him to give him credit for that. So the general design of that is what they did was they took a long glass tube, and we're talking like, pretty big. And so we're talking probably at least a meter long, and it's got little kind of marks on it every millimeter or meter or centimeter probably. And what happens is they filled up this tube of mercury all the way, sealed the end that was open, and flipped it upside down and let it sit in a pool of mercury. So you can imagine I've got this dish of mercury with a fully submerged tube of mercury kind of sticking out of it. And you can kind of see the picture here. So what happens is when the atmosphere, and the trick is that you need to have this pool here exposed to the air pressure. And what happens is when air pushes down on, because of the atmosphere, so atmospheric pressure, when air pushes down on that mercury, it forces mercury up into the tube. And if the air pressure is lower, it doesn't push down as much and mercury comes out of the tube. So depending on what's going on with the weather on any given day, you have air that's pushing mercury up or down. And the measurement is literally the height of the mercury column. So one of the units you're going to see is called millimeters of mercury. It's literally how many millimeters of mercury we have in our tube. Okay. Obviously, having a giant pool of mercury sitting around is not the best plan in the world. So there are new ways that we have that now. We have what's called a bellow, and it's like an expandable kind of accordion type container. And then the volume of gas that's in there will expand or contract depending on atmospheric pressure. Generally, the way it works is that if we have high atmospheric pressure, it means that we have good weather. If we have low atmospheric pressure, it usually means that we have kind of crappy weather. And so they use the different changes in pressure to indicate the type of weather that's coming. So that's kind of one tool that you can kind of use for that. Interestingly, a side note is that air will move to areas of from high pressure to low pressure. So like if you ever walk into a building and you feel a big gust of wind, that's because there's a difference in pressure from your outside area to where you were coming from. And it always goes from high pressure to low pressure. And you need to make sure that you know that. So like even wind, the direction the wind blows has to do with the differences in pressure. So if we have one area, let's say here in my hands are a map. If I have a high pressure area here and a low pressure area here, the air is going to move from the high to the low pressure area and your wind is going to blow that direction. So if you have winds out of the northeast, it means that there's higher pressure in the northeast or northeast, and then it blows from the northeast to the other direction because that's the way that the pressure differential is making it go. When we talk about gases, we kind of predict how they behave via something called the kinetic molecular theory. So it just explains kind of how particles move around. And there are 4 components of it, and 2 of them are very important, and the others aren't quite as important. So it's not that they aren't important, it's that they kind of behave or dictate what happens more. So the first one is that gases are made of tiny particles so small that their size is negligible when compared to the distance between them. So what that means is that if you could take out a teeny tiny ruler and measure the size of a particle and then measure the distance between that particle and another one, the distance between them is so big that the size isn't super important. And that just tells us that if I say I have a 2-liter container of gas, I'm just going to say that my whole gas is 2 liters. I'm not going to take out the volume of those particles. Okay. The second component is that all collisions between a molecule of gas and another molecule or the sides of the container are an elastic collision. And what that means is that if it hits it, it doesn't lose any energy because it hits the container or hits another particle. Now, this is a very idealized model and is most true when gases are at low pressure. So we're not trying to squish a ton of gas molecules together, or higher temperatures. So for this rule to kind of apply and be our most idealized gas, you need to have our molecules moving fast so they can smash into each other really hard, and they need to have lots of space to hit each other, because if you take a gas and you put it under very high pressure, intermolecular force things start to happen where we start to get some attractions, and then our gases don't behave the way they're supposed to. The same thing happens when we get our particles cold. Cold particles are going to want to stick together more because they're not moving around as fast, and that's going to cause problems as well. Okay, these are the bigger ones, these 2 components here. So gas molecules are in constant random motion. So that means that if I have a gas particle, I cannot predict which direction it's going to move or what it's going to do. And what happens is the pressure that we measure of a gas happens when the particles collide with the sides of the container. The more collisions there are, the higher the pressure is going to be. It's not the collisions with each other, it is the collisions with the container. Okay, sorry about that. You might see a weird editing blip. My dog was about to bark at me, so we'll come on back into this. So last component of kinetic molecular theory is that at any given temperature, all particles have the same average kinetic energy. We'll get more into the kinetic energy thing when we talk about Graham's law and Boltzmann distributions, but the general idea is that if I have any particle, regardless of what type of gas it is, helium, hydrogen, nitrogen, whatever, they are going to have the same kinetic energy if they are at the same temperature. And particles that are at a higher temperature have a higher kinetic energy, and particles that are colder have a lower kinetic energy. So when we talk about their speed, particles that are hot are moving around faster, particles that are cold will move around slower. And that also affects the pressure, which you'll see in the simulation we're going to get into. All right, when we talk about pressure, there are a number of units that you are going to have to be comfortable with and comfortable converting back and forth to. Your equation sheet shows some of these units, so you don't have to have all of them memorized, but you do need to know kind of what they are. So units to measure pressure could be in pascals, and a pascal, to give you a sense of how much that is be like if you took a bar of soap and then took the weight of that bar of soap and distributed it over 1 meter square, okay? Atmospheres are another unit. By the way, pascals are PA for their abbreviation. Atmospheres are another one, and they're ATMs. You probably are familiar with pounds per square inch, PSI. That's the one we don't use in this class, unfortunately. There's torr, which is the Torricelli unit from before. There are millimeters of mercury, which is the height of that column, and there are inches of mercury, which is just, you know, America. We're going to use inches instead of millimeters. So it's literally just the conversion between millimeters and inches. And if you need to know, there are 2.54 centimeters in an inch. So there's 25.4 millimeters in an inch. Now, standard values are kind of our benchmark values for a normal average day that they sent. And they are 1 ATM. So if you see the pressure measured at 1 ATM, that's considered standard pressure. 101.3 kPAs or kilopascals, that is the value for the Pascal unit. These two numbers are the same. So 1 atmosphere is equal to 101.3 kPAs. They are the same pressure. 760 torr, 760 millimeters, and 29.92 inches of mercury. 14.7 PSI is equivalent to your standard pressure, but like I said, we generally do not include that one, but I just want you to know for reference. So when we talk about these 1 ATM, 101.3, 760, 29.2, all of those measure the same pressure, and that's what scientists have set as standard pressure. Now, there is a standard temperature as well, and it's 273 Kelvin. Now, Kelvin, the temperature scale, we haven't necessarily talked about yet, but what it is it's a temperature scale that kind of runs parallel with the Celsius scale, but instead of having 0 set at the temperature where water boils, it's the temperature where absolute 0 happens. So 273 Kelvin is equal to 0 degrees Celsius, and they are kind of easily transferred. 1 Kelvin unit is the same as 1 degree Celsius. So if I were at 1 degree Celsius, I would be at 274 Kelvin. To get back and forth, to go from Celsius to Kelvin, you would subtract, nope, I lied. You would add 273. To go from Kelvin to Celsius, you're going to subtract 273. So your number for Kelvin should always be larger there. Okay. Now, when they talk about gas experiments, a lot of them are performed at what they call STP. And STP stands for standard temperature and pressure. And that is any of those pressure values from before, as well as 273 Kelvin. So if you see that experiments happening at STP, these are your conditions. 1 ATM, 273 Kelvin. 760 torr, 273 Kelvin. So we're going to kind of be going back and forth with those. Up next is going to be a simulation that we're going to play around with so you get an idea of how gases behave, and then we'll get into the math. If you have any questions, let me know. Otherwise, good luck.